Hello everyone, welcome to Analog Electronic Circuits, lecture number 19, part 2. Today we are going to start with a new topic on Darlington pair. So Darlington pair is a multi-transistor configuration. Later on we will prove that it's a super beta transistor. It's called as a super beta transistor, which provides a very large current gain. Now Darlington pair was named after the engineer Sydney Darlington. It is invented at Bell Labs in 1953. So let us look at the configuration and the structure for the Darlington pair. How does it look like? So let us begin. Let me use a black color to draw the structure. So draw a simple NPN transistor. Okay. So this is my simple NPN transistor. Now I'll mark its collector, base, and emitter. So the emitter, this let me call this as transistor as Q1. So the emitter, from the emitter of Q1, you connect it to the base of Q2. Okay, so here it is. And the collector of two transistors have to be tied together. So collector of Q1 and Q2 will be tied together. And then later on, this becomes my base now. So let me use a red color to mark it. This becomes my base terminal. This becomes my emitter terminal, and this becomes the collector terminal of the composite transistor now, right? Now let me mark the various things. This is base 1, collector 1, emitter 1. This will be base 2, collector 2, and emitter 2. Let me also mark the various currents. So voltages will be here, it will be plus minus VBE1, and here it will be plus minus VBE2. All right. Now the current which is entering into the transistor, we can call that current as a input current, right? So let me mark over here. This is flowing into the base terminal. This current is called as IB1. Let me highlight it using a yellow color. And this current is called as my input current. So what is the output current for this configuration? So here IE2 which is flowing, IE2 which is flowing into the emitter 2 terminal is called as the output current. What about the intermediate currents? So here the current which is flowing is IE1, and here the current which is entering the base terminal is IB2, right? So now here we have VBE and VBE2. So the total VBE will be VBE, capital VBE, which will be VBE1 plus VBE2, right? All right. For a Darlington pair, your base to emitter voltage is equal to the addition of individual transistors base to emitter voltage. So the VBE, the overall VBE of the Darlington pair will be VBE1 plus VBE2. So this becomes my Darlington pair, right? This composite arrangement of two transistors Q1 and Q2 becomes my Darlington pair, which I can, mark it. I can draw it again using a composite transistor, just as a single transistor, just a symbolic form. This will be collector, we can mark it. This is base, and this is emitter. And we call this transistor as QD, standing for Darlington transistor, wherein the beta, just now we will prove now, the beta of the Darlington pair, beta D, will be product of the individual transistors current gain, that is beta 1 into beta 2. All right, so that is what we will show. Now, since we are using a Darlington pair, having a higher value of VB is an advantage or a drawback? It's a big drawback. Okay, what is VB? Your VB is the value. Here it is in the input characteristics. So input characteristics look something like this, right? So over here we have VBE and IB. So VB more value means what? It will take more voltage to turn on. right? So that's a drawback, right? So transistors should turn on at a very low value of VBE. So if you have twice the value of VBE, if you have VBE1 plus VBE2, then the transistor will take some extra voltage to turn on, and that's a drawback, right? Now let's derive the current gain of this configuration. Now what is the current gain of this Darlington pair? Output current upon input current. Your output current is IE2 and input current is IB1. So let us write it down over here. AI, which is the current gain. This is the current gain of Darlington pair. Okay, so what is this AI given by? AI will be given by output current, that is IE2, divided by input current, which is IB1. All right. Now IE2, I can write in terms of IB, right? How can I write it? Let me just clarify this term. So IB is IC, I mean IE is nothing but 1 plus beta times IB. We know this relation, so we'll use this over here. So we can write further, this will be 1 plus beta 2 times IB2 divided by IB1. Now what is IB2 equal to? From the diagram, your IB2 is nothing but, now IB2 is nothing but equal to IE1. And what is IE1 can be written as 1 plus beta 1 times IB1. So now what we'll do is we'll replace IB2 with 1 plus beta 1 times IB1. So I can write that is AI, which is the current gain, is given by 1 plus beta 2 into IB2 will be replaced by this term over here, right? So let me mark this. So this IB2 will be replaced by this term over here. Okay, fine. So let me write 1 plus beta 1 into IB1 divided by IB1. Now IB1 and IB1 will get cancelled. And finally, what are you getting? 1 plus beta 2 into 1 plus beta 1. All right. So if we assume the value of beta, it's beta 1 actually over here. Yeah. So if you consider 1 plus beta approximately equal to beta, because your beta value is very much greater compared to 1. It's 200 to 300 for a normal BJT transistor, right? So here AI will be given by, AI will be approximately equal to beta 1 into beta 2, right? So this is the formula for the current gain. This is the, let me write, current gain of Darlington pair transistor. It's famously called as Darlington pair. It's current gain, it's of a very high value. Now in normal multi-transistor like in cascade and cascode, the current gain is not so much high. But in this case, let's take an example. Let's take an example that beta 1 is equal to beta 2 is equal to 200. Then what will be my AI value? So AI value will be approximately equal to 40,000, which is very, very high value. Okay, so it is providing a high voltage gain. And if my transistor Q1 and Q2, so over here, if my transistors Q1 and Q2 are symmetric, and normally they are symmetric, right? So if Q1 and Q2 have similar parameters, so Q1 and Q2, if Q1 and Q2 are matched, then we can write beta 1 is equal to beta 2 is equal to beta, and VB1 is equal to VBE2. In that case, my formula will modify as follows. It will be AI, which is equal to beta square. That's why over here, if you can see over here, in case of this Darlington pair symbol, we have written beta d is beta 1 into beta 2, right? So that was the current gain. All right. Therefore, since it has a very high value of now, beta value is normally in terms of 100 or 200. So 100 square, 200 square is a very large value. So therefore, your Darlington pair, therefore, the Darlington pair is also known as super beta transistor, is also known as super beta transistor. Let me highlight it. Okay, let me highlight the formulas also. Yeah, so this is my current gain for a Darlington pair. So if they ask you this question about the Darlington pair, prove that the current gain of the Darlington pair is equal to the individual transistor current gain. So you have to do the simple derivation. Draw this Darlington pair, right? So this is your Darlington pair. Darlington pair transistor. So it's nothing. We have connecting two NPN transistors. So emitter of the first NPN transistor is connected to the base. Their collectors are tied together, and we have three terminals: base, collector, and emitter for this Darlington pair transistor. All right. Now we have to analyze this Darlington pair and fit this Darlington pair in one of the amplifiers, right? And we'll analyze that amplifier. So let us start with that analysis. So we'll write over here. We have to fit this Darlington pair in some configuration. So we'll use common collector configuration. So we'll write common collector Darlington amplifier. Common collector amplifier using Darlington pair. Okay, or common collector or emitter follower. Any name will do. Common collector or emitter follower amplifier using Darlington pair. So this will be our heading now, and we'll analyze the amplifier circuit using the Darlington pair configuration. Right. All right. So let's start building up the circuit. Now, do you remember how does the common emitter follower configuration looks like for a single stage amplifier? So let me draw it quickly. So if I have a single stage amplifier, my common collector or my emitter follower looks something like this. So your collector is directly connected to VCC. Then we have R1. Here we have input coupling capacitor, and here we have output coupling capacitor CC2. This is RE, R1, and here we have a ground. Here we have V in, this is CC1, and this is V out. So in a emitter, this is your emitter follower. Let me use it a black color. So this is my emitter follower circuit, right? So this is the circuit which we have to make using Darlington pair now, emitter follower. So in an emitter follower, the input is applied at the base terminal. Input at base, and output is taken from the emitter. So output from emitter. So that is what we have to remember, and we have to replace this BJT by a Darlington pair. All right. So that is what we have to do. Our job is very simple. So let me begin. So first of all, I will draw the Darlington pair itself. So Darlington pair again, take a transistor, NPN transistor, and from the emitter terminal, draw connected to the base terminal of Q2 and tie their collector terminal together. Right now, this becomes my Darlington pair. Okay. So now I have to connect the rest of the circuit. So I'll use a different color. I'll use a blue color to connect the remaining part of the circuit. So this is my R1. This is R2. Over here it should be R2. Then we have RE. Okay. Then at the output we have a capacitor. So here we can say we have ground. Here also we have a ground. This is CC2. This is plus minus V out. Okay. This is register R2, R1, and here it will be directly going to the VCC. So here I'll connect the VCC plus VCC. Here I will have RE, and over here I will have RSig. I can consider RSig resistance. That is absolutely fine. But let me see later on, we will be using RSig resistance. Yes. So let's connect RSig resistance over here. This is RSig, internal resistance of the voltage source, and a capacitor, input coupling capacitor. All right. So let's proceed forward now. Here, let me connect the input. That input we call it as plus minus Vs. So this input is AC. This VCC is my DC quantity, and my V out is again a amplified AC quantity, right? In this case, since it is a common collector or emitter follower amplifier, the voltage gain of the circuit will be almost unity, okay, or less than that. And here I will call this terminal as base. This will be the collector, and this will be the emitter of the overall composite transistor, right? Now, this is how the circuit diagram looks like. For a emitter, you can compare it with this one. Only thing what we did was we have connected, instead of single BJT, we have connected as a Darlington pair unit. Is that fine? Yeah. So please note down the circuit diagram. And for this amplifier, again, we will do the following analysis. We will be doing the two types of analysis over here, DC analysis. And DC analysis will find the Q point, and we'll do the AC analysis. In AC analysis, we can find the voltage gain, we can find the input resistance and the output resistance of the circuit. So now let us start directly with the DC analysis. So let me add the heading over here. DC analysis of Darlington pair. Of we can write it's all under the heading of Darlington pair. Emitter follower Darlington amplifier using Darlington pair. So what do we do in the DC analysis? In the DC analysis, we open circuit all connected capacitors. We open circuit all connected capacitors. So what is left out in the circuit? So this CC1 and this is, I forgot to write, this is CC1 and this is CC2, input and output coupling capacitors. This will be open circuit. So what will be left out? R1, R2, RE, and the two transistors, Darlington pair, will be left out, right? So let me redraw the circuit over here. So let me use a black color again. So I am drawing two transistors, Q1, and over here Q2. Their collector terminals are tied together, right? And that collector is connected to VCC. Then we have register R1, register R2, and register RE. So this is connected to the ground. This is connected to the base terminal, and this will be connected to VCC. R1, R2, emitter, RE, right? Now over here, what happens is it's very difficult to do the analysis further because your base current IB1 flowing into Q1 transistor is not equal to 0. So IB1 is not equal to 0. Maybe it's a very small value. Now this is the base terminal, right, of Q1 transistor. We can call it base 1. So what do we do is we apply the Thevenin's equivalent at the base terminal, right? We applied the Thevenin's theorem at the base 1 terminal. So after applying the Thevenin's theorem, we know what do we get. So at the base terminal, it's replaced by Thevenin's equivalent voltage, which is VTH, in series with Thevenin's equivalent resistance, that is RTH. And the remaining part of the circuit remains the same. So we'll have Q1 over here, and then here we'll have Q2 transistor. You have a resistor RE from here, and their collector terminals are tied together. So let's tie their collector terminals together, and that is connected to VCC. All right. And here we will have VTH and RTH. Now we know VTH and RTH. I mean, let me mark the terminals over here. This is base 1, collector 1, emitter 1. This is base 2, collector 2, emitter 2. Let me add the ground also over here. Okay, so we have to analyze this network. First of all, what is RTH and VTH? So RTH will be R1 parallel to R2. You can check it out later. And what will be VTH value? VTH value will be similar to what we have done earlier. It will be R2 divided by R1 plus R2 into VCC. So that is the Thevenin's equivalent voltage and Thevenin's equivalent, voltage and Thevenin's equivalent resistance. Now, for this circuit, let me mark the value of various currents and voltages. So let me use a blue color. So here the current flowing to the base 1 terminal will be IB1. All right. Here the current flowing to the emitter terminal will be IE1. Current flowing to the base 2 terminal will be IB2, and the current flowing through the emitter 2 terminal will be IE2. So these are the currents. Let me mark the voltages. So here it will be VBE1, and from here to here it will be, okay, let me show the current above here. This is IB2, and here plus minus, this is VBE2. So what is the overall base to emitter voltage for this Darlington pair? If I consider VBE1 and VBE2 same, if Q1 and Q2 are matched, Q1 and Q2 are matched. That's an assumption. So if Q1 and Q2 are matched, I can say, what can I say about VB? So I can say that VB1 is equal to VBE2. And further, I can say beta 1 is equal to beta 2. So over here, originally VBE1, VBE is VBE1 plus VBE2. And if they are same, that will be equal to twice VBE1. Okay, since they are similar. And what is the other observation we see? We see that your emitter 1 current is equal to base 2 current, right? So I can write from the circuit, I can write IE1 is equal to IB2. So these are some of the observations which will help us to write the, calculate the Q point. Now let's calculate the value of IB1, right? IB1 we can easily calculate by applying the KVL to the base emitter loop. So let me mark with yellow color which is the base emitter loop. So here it is, arrow over here. So this is the base emitter loop. So let me write over here KVL applied, applying KVL, applying KVL to base emitter loop. So what do we get by applying KVL to the base emitter loop? We have VTH minus IB1 into RTH minus VB1 minus VB2 minus IE2 into RE is equal to 0. All right. So let me add over here. And, from the early analysis also we'll use the result. Let us wait. So let me write the equation. It is VTH minus IB1 into RTH minus VBE1 minus VBE2 minus IE2 into RE. Now I can write IE2 in terms of IB1. How? Now from this diagram, it's very simple to understand. IE2 is nothing but, okay, just wait. IE2 I can write in terms of, let me add it over here quickly. IE2 I can write it as 1 plus beta 2 times IB2. And what is IB2? IB2 is IE1. So I can further write it as, this will be 1 plus beta 2 times IE1. Correct? Now IE1 can be also 1 plus beta 1 times, this also can be 1 plus beta 1 times IB1, right? So I can write IE2 is equal to 1 plus beta 2 into 1 plus beta 1 times IB1. All right. And since beta is very much larger as compared to 1, your 1 plus beta can be approximated as beta. So I can write IE2 as beta 1 into beta 2 approximately as into IB1. So this IE2 I'll replace over here. Okay. From here, I'll substitute it over here. All right. And this, instead of writing beta 1, beta 2, I can call this as beta D. Now beta D, where beta D is beta 1 into beta 2. So this is the individual transistor Q1 and Q2 current gain. And D stands for, this is the Darlington transistor current gain, right? So now let me rearrange the terms over here. Now also we note that VBE is VBE1 plus VBE2. So here I can add the two terms together. I can call it VBE. So here I will write VTH minus IB1 into RTH minus VBE minus beta D times RE into IB1. We have replaced IE2. We have replaced IE2 by beta D times IB1. Here it is. Okay, fine. And now I can club all the terms of IB1 together. So IB1 will be equal to VTH minus VBE divided by RTH plus beta D times RE. So this is the equation for IB1. And here we can write where VBE is nothing but VBE1 plus VBE2, and beta D is nothing but beta 1 times beta 2. So once we know the value of base current, we can easily find the value of collector current. So collector current will be, IC1 will be beta 1 times IB1. Okay, so we got the collector current now. And now we can apply, so this is the Q point, right? ICQ is the Q point. Now we can apply the KVL to the output loop. That is, where is the output loop? Collector emitter loop. So let me show it to you with green color, my collector emitter loop. So over here, this is the collector to emitter loop. So applying the KVL over here to the collector emitter loop, what do we get? VCC minus VCE2. Okay, here there is a VCE2 present over here. I am not shown it, plus minus VCE2 and minus IE2 into RE. All right. So let me write over here, applying KVL, to collector emitter loop. So applying KVL to the collector emitter loop, what do we get? We got VCC minus VCE2 minus IE2 into RE. is equal to 0. Okay, all right. Now from here we can easily calculate VCE2. That is VCE2 is the other value of, I mean, ICQ and VCQ are the Q point. So VCC minus IE2 into RE, right? So that's the expression for VCE2. Now, if I want to calculate IE1, how will I calculate IE1? So IE1 will be IC1 plus IB1. Is that clear? Or also we can write IE1 is also equal to IB2 from the circuit diagram. Here you see your IE1 is also equal to IB. So that you need to remember. And how will you calculate IC2? So once we have the value of beta 2, we can calculate the value of IC2 as beta 2 times IB2. All right. And if suppose I have to calculate VE2, let's say I want to calculate VE2. So VE2 will be IE2 into RE. Okay. So let me add over here. If we wish to calculate VE2, it will be IE2 into RE. So these are all the DC parameters which we can find out. And yeah, now, yeah, these are all the things which we can find out: the Q point, then the terminal currents and the voltages, right? So this completes the DC analysis for Darlington pair. I mean, for the emitter follower or the common collector amplifier using Darlington pair. Now, for the AC analysis, we will take a separate lecture because we don't want to spend too much time and it will create some kind of confusion if we continue with this further, because it will take a long time. So that's why we are dividing into two parts. In today's session, we have started with, let me revise what we have done so far. Okay. So this is lecture number 19.2. Let me add over here point A. Okay. Or 19.2.1. Because I'm dividing this into two parts. One will be AC analysis, other will be DC analysis. So we started with the introduction of Darlington pair, and we saw that it really provides a very large current gain. This is the Darlington pair configuration, right? We have shortly proved that in the Darlington pair, the current gain is the product of the individual current gains. So you get a very high value of current gain in case of a Darlington pair. And your Darlington pair, that's why it's called as a super beta transistor. Then we have identified a configuration, that is emitter follower amplifier employing Darlington pair. So this was the circuit diagram, and we were supposed to do DC analysis and AC analysis, but we completed the DC analysis part over here. So in this part, we have we have open circuit all the connected capacitors, and then we are left out with the DC equivalent circuit. So over here, we applied the Thevenin's equivalent at the base 1 terminal, and this is the circuit we got. Over here, we assume that Q1 and Q2 are mass transistors, so their parameters are similar. And we, by applying KVL at the input loop, base emitter loop, and KVL at the output loop, we calculated the Q point, which is as follows. Right, so this will be helpful by solving the numerical. And now we would like to end this session over here. And next time we will continue our discussion on Darlington pair, but we'll start with the AC analysis directly, right? So this is the circuit diagram. So over here today we have completed DC analysis part. So this is completed. This we will do it next time, AC analysis. Okay. So that's all for this session. Thank you everyone for joining. And for further analysis of AC analysis, you all wait for the next session. So until then, have a good day and thank you.